a ball of mass 2.4 kg moving horizontally with a speed of 3 meters per second collide with a second ball of mass 1.5 kg moving in the opposite direction with a speed of 5 meters per second. The first ball bounces off the second ball with an angle of 60 degrees below the horizontal at a speed of 1.5 meters per second, while the second ball bounces above the horizontal. What is the speed of the second ball? Okay. Now, what will be the final speed of the second ball, which we've named as v? Well, when we look at this kind of collision, they are moving in the x-axis, but after collision, they are thrown both of them at a certain angle. And so, there is momentum conserved in the x-axis and momentum conserved in the y-axis. What we need to get to understand is whatsoever type of collision that we can talk about, momentum is always conserved. But in such a collision as this one, kinetic energy is lost. Momentum is always conserved. Well, even if kinetic energy is lost, energy itself as a whole is conserved. So let's start with the first one. So let's call this as our m1. This is our mass 1, the 1.5 kg. Then this is our mass 2. Okay. And so if we start working in components, so start first in the x-axis. The conservation of momentum, that is m1 u1 plus m2 u2 should be equal to m1 v1 plus m2 v2. So this, we are talking about the x-axis, and so these are all x components. All the velocities we are using here are x components or the velocities. And so m1, as we can see, the mass is 1.5, the velocity, the initial velocity is 5, so that would be 1.5 multiplied by 5. And then mass 2, the mass is that, the velocity is that, but because it's moving in the opposite direction, the velocity is going to be -3. And then we have got mass 1 still, that is 1.5. Well, at what velocity did mass 1 bounce? We don't know what velocity it bounced, but what we are getting is the x component of this velocity, because we are working in x components. So how do you get the x component of that velocity? So let's call this as v1. So that would be v1 cos theta. Okay. Now we are going to take, yeah, that would be cos theta because it's going forward like that. We are taking the x component of this velocity. The x component goes like that. The y component of that one goes up. As we can see, the ball was moving in that direction up. Okay. And then we go to m2. Well, if we consider m2, m2 is moving in the opposite direction. The mass is that, the mass is 2.4. And then the x component of the velocity is v2 cos. Now the angle it is making is here. That is cos 60. Now notice that m2 is going like this. If we take motion going in this direction as positive, I mean that is m1 going in that direction, m2 is going in this direction, and so even this x component of the velocity is supposed to be negative, and so we are going to add the negative there. Alright, so we go on and multiply 1.5 multiplied by 5, that is a 7.5, and then we're going to also add the product of 2.4 and -3. So this side is giving 0.3, and that should be equal to 1.5 v1 cos theta. Again, we can just take cos 60. So cos 60 is 0.5. 0.5 multiplied by 2.4, which we can see here. Remember, it is negative there, so it's giving -1.2 v2. Okay. Now, of course, we know v2. We know that this second ball bounced at what velocity? Okay, which one do we... Okay, it's a second ball, the 2.4 kg mass bounced at that velocity of 1.5 kg. Actually, I can just replace direct at that point instead of saying -v2. So I'll say okay. So that is negative. The velocity is 1.5 cos the angle is 60 degrees. And so go on direct and say 1.5 multiplied by cos 60, that is 0.75, and then we're multiplying that by what is outside there, the 2.4. Remember that is negative, so that is negative 1.8. So that is it. Now we are going to take this value to the other side so that we just remain with this portion, and so that is going to give us 1.5 v1 cos theta being equal to 0.3. Well, I'm taking this portion the other side, and so it's going to become positive 1.8. So that gives me 1.5 v1 cos theta is equal to 0.3 plus 1.8. That is a 2.1. So let's divide by 1.5 on both sides. And so v1 cos theta is going to give us that is giving us 1.4. So this is v1 cos theta. This is what we have gotten in the x component. So let me just write here v1 cos theta is equal to 1.4. So after finding the value in the x-axis, let's go now in the y-axis, because even in the y-axis momentum has to be conserved. Momentum before impact should be equal to momentum after impact. So in the y-axis, same, m1 u1 plus m2 u2 should be equal to m1 v1 plus m2 v2. So all these are in the x-axis. Now mass 1, of course, as we can see, this mass 1 was just moving in the x-axis. It doesn't have any component of the force of velocity in the y-axis. It was not moving up, not moving down initially, and so the momentum before impact is 0 for mass 1. As we can see, even mass 2 was just moving in the x-axis like that. It wasn't moving up or down initially, and so even the momentum before impact in the y is 0. Okay, now let's go to mass 1. Mass 1 is 1.5. Now the final velocity of mass 1 before impact, what will be it? Well, I mean after impact. This is the final velocity after impact. So after impact, the velocity we're talking about is that one. So it is v1, but because we're talking of the y component, we are going to take sine theta. So let's take motion going up as positive, and that which is being released down as negative. So because mass 1 went up, so we are going to take it positive like that. Okay, what of mass 2? Mass 2, the mass is what? The mass is 2.4. What of velocity? Now you can see it bounced at 1.5, so we're going to get the y component of 1.5, but because it went down, we're going to put a negative there. That will be negative 1.5 sin, the angle is what? The angle is 60 degrees. Okay, so this side is 0, and then we have got 1.5 v1 sine theta, and then sin 60 times 1.5 times 2.4. So this value is giving negative 3.11769. Okay, we can take it the other side and it's going to become positive, so that will be 1.5 v1 sin theta is equal to 3.11769. Well, let's divide by 1.5 on both sides. So v1 sin theta is going to give us, that's about 2.0785. Okay, so we know v1 sin theta and we know v1 cos theta. So the question is, what is the final velocity of the second ball? Well, let's put it that they even asked us to find the angle. So if they had even asked to find the angle, we know that sin theta over cos theta is supposed to give us tan theta. So we're going to divide the portion which has got sin theta with the one which has got cos theta. So we'll go say v1 sin theta, which is equal to what? 2.0785, and then we're going to divide it by v1 cos theta, and that is equal to what? 1.4. So v1 and the v1 will cancel. Sin theta over cos theta, that will give us tan theta, and so that is going to be equal to 2.0785 divided by 1.4. That is 1.4846. Now I want to remain with theta, so we're going to take the tan inverse of the value which we have here, 1.4846. So the angle there is 56, just about 56 degrees, 56.0, where we can just name it as 56 like that. Okay, so that is the angle at which it bounced going up. Now we want to find v1 sin okay, we want to find the final velocity at which the ball bounced. So what we can do is we can use one of these equations, either this or that. Any of them is going to give us the value. So if we use v1 sin theta is equal to 2.0785, we'll find that v1 is going to be equal to 2.0785 divided by sin. Now the angle theta is about 56 degrees, so v1 is going to give us 2.0785 divided by sin, that one. Okay, so the angle is, the velocity is 2.5. Let's just say 2.5. Okay, that would be meters per second. Well, that is the velocity at which it bounced, 2.5. Alright, now having seen this is the final velocity of the first ball at which it is going to bounce. Well, since we found the final velocity, now the second portion, how much kinetic energy is lost in this collision? So how much kinetic energy is going to be lost in the collision? Let's go on and find that. So let's keep that velocity, the 2.5 velocity which we have. So we can just put it there, 2.5 meters per second. Now how much kinetic energy is lost? So to find the kinetic energy which is lost, we are going to first find the kinetic energy initially of the two balls. So kinetic energy initial will be the sum of the kinetic energies of the two balls. That will be half m1 v, so we're taking u first, u1 squared plus half m1 m2 u2 squared. So m1 is 1.5. The initial velocity of m1 is 5 squared, and then m2 is 2.4. The initial velocity, where we are not interested in the direction, even if we were interested in the direction, because we are squaring this, even if we had put a negative there, it will still cancel out. So we are finding the energy and we are not interested in the direction really. So we are going to go on and punch that. So we've got half multiplied by 1.5 multiplied by 5 squared, that is about 18.75, and then we've got half multiplied by 2.4 multiplied by 3 squared, that is about 10.8. So if we do add those two, we are going to get around 29.55. Okay, this is the initial velocity, the initial kinetic energy of the two balls together. Now let's find their final kinetic energies as a sum. So same formula, half m1, but here we are using the final velocities, v1 squared plus half m2 v2 squared. Wow, so half m1 minus 1 is still 1.5. It bounced at what velocity? At 2.5 meters per second. And then half minus 2 is 2.4. And then we know it bounced at this velocity of 1.5. so that squared. So this is going to give us half multiplied by 1.5 multiplied by 2.5 squared, so that is around 4.6875. And then you have got the other one, half multiplied by 2.4 and then multiplied by 1.5 squared, so that is 2.7. So if we add those two values, 4.6875 plus 2.7, that is giving us 7.3875. Now, according to conservation of energy, not really kinetic energy but energy initial should be equal to energy final. Now, energy initially, the only kind of energy that we had was kinetic energy, and so 29.55 should be equal to, now at the end after collision we had kinetic energy 0.7.3875 and also some loss, okay, because the energy at the end and the energy at the beginning should be the same. So this value is not the same as this one. So there is some loss, and that loss is what we want to find. And so we're going to take this 7.38 over the other side to find the loss. And so the loss is going to give us 29.55 minus 7.3875. So let's see, 29.55 minus that answer. So the loss was actually 22.16 joules. Since this is energy, it is going to be in joules. So that is how much energy was lost in this kind of collision.